lumped capacitance. It's okay, I'm gonna go over the note. I typically do this, write all these things on the board and you copy, but I heard from students that people don't tend to take notes on paper during online lectures. So what I'm going to do is to go over these notes that are the ones, the key notes to prepare for your exams. And actually, I think they're very good for your professional life too. And I'm going to be highlighting the parts that matter. And these, you'll have already had the first read at them, so that should be quite convenient. Okay, so in the whole point of lumped capacitance is that in lumped capacitance, it applies when the temperature inside a body is constant, not constant in time, but constant in space, such that the surface has a temperature, but the center is at the same temperature, and different parts of the surface are at the same temperature too. Of course, that never happens. That's a lie. However, in so many cases, we are so close to this ideal model that we assume it's ideal and the math is super simple. The reason the math is good in this case is that because we have no conduction, we don't need to worry about the equation of heat as heat moves as a vector inside the body, because heat does not move inside the body in the lumped capacitance methodology, because it's all at the same temperature and I have no gradients to drive the heat. So when lumped capacitance applies or it doesn't, we're going to look at that next week. Right now, we're just saying if it applies, this is the way we go about it. And the reason we go about it, we do it this way, because it applies when we can neglect conduction. But to know when I can neglect conduction, we need to get deeper into conduction. Right now, it's only control volumes and heat transfer mechanisms. That's all we need, which we have already seen. And the steps we're going to follow are these four we have here. We are going to determine a control volume and an energy balance, just like we did in the first week. Then we're going to assign to the Q in and the Q out, and we're going to assign expressions based on the heat transfer mechanisms present. That's what we saw in week 2. Now, what is new here is just that when we put it all together, what you're going to see, we obtain an equation. And that typically is a first order ordinary differential equation. I know many of you love that, right? But it is okay, because we have very mechanistic ways of solving those equations, and I have uploaded where it's a math refresher in the topics of class at the very last one, some strategies for solving differential equations. There are many. I just put there the ones I use myself, but if you want to use any other methodology of the classes you took on Calc, that's perfectly fine. And of course, we writing the equation actually is relatively simple. It writes by itself. Then we have to solve it. And for that, we have these mechanistic approaches. So let's consider one example. And again, I'm not assuming you know anything about this class, but you will know, for example, that if I have a hot sphere in colder air, the sphere is going to cool down. That is fair, right? I have something hot in cold fluid, it's going to cool down. And I'm putting some numbers here. So I'm assuming that is a sphere made out of copper of 6 centimeters in diameter, and that the sphere is initially at 90 degrees C, so it's fairly hot. is like similar to the problem we did in the first seminar on last Monday, a week ago. And this is putting stagnant air in a room at 20 degrees C. That means there is no forced air. Therefore, we'll be talking about the mechanism of natural convection and not forced convection. And just for now, because we are learning, I'm going to assume my stock heat transfer coefficient for natural convection of 10 watts per meter square Kelvin. You will know exactly what heat transfer coefficient to use about halfway through the class. But right now we're going to call it 10. You're going to see it's more or less 10 anyway. But right now I'm just giving it to you. Here's the density of copper, and here's the specific heat of copper. So I would love to do this. Okay, I'll give it a try. I'm looking at the chat, and I would like to see who can guess in this problem in which 90 degree, a copper sphere 90 degrees C is put in air at 20 degrees C. Question number one, before I teach you anything, is what is the final temperature of the sphere going to be after a long time? I would love to see anybody venture a final temperature in the chat. Of course, same as a room. You see, this is something that has important implications for the math eventually. But you don't need to take this class to know that eventually it's going to go to room temperature, 20 degrees. Great. So, of course, I didn't say some things like the room is large enough such that, yeah, the sphere is not heating up all the air in the room, right? In suggesting 20 degrees C, you assume some things. But if I say nothing else, you assume whatever is convenient to you, right? And as long as it is reasonable. So we have determined that the sphere is eventually going to be at 20 degrees C at the end. Second question, and I have it in the notes here, is what is the rate of heat loss of this sphere? We know it's losing heat because it starts at 90 degrees, is going to end up at 20 degrees. It's losing heat. How fast is losing heat at the beginning? Now, this is a very engineering question that has very important implications, has a very straight answer. But when I ask it as engineering, it can be intimidating. So we are talking about what is the rate of heat in watts that is coming out of the sphere into the air. Might sound scary. And of course, like now it would be much more difficult to ask the question through the chat. But here we go. The heat that is going out by convection. This is what the problem is telling me. Consider a natural convection coefficient. If I wanted, I could add radiation too. And you're going to see later I have a problem with radiation. Let's for now consider only convection at 10 watts per meter square Kelvin. So the heat losses by convection are surface area times the heat flux by convection. This heat flux by convection, we saw it. This exam is open book. And when we have normal classes not online, you also have a formula sheet. But the truth is that this is something that you will very soon know by heart. That is that the heat loss is proportional to the difference between the surface temperature and the fluid temperature. And the coefficient of proportionality is H, the heat transfer coefficient. So up to equation 3 here, this is something very simple based on the equations we saw last week. So so the area of the sphere is 4 pi r squared, which is also in the formula sheets, which you already have access because you have all the exams from previous years with the formula sheet and with the worked out answers, right? And the temperature I asked about the initial rate of heat transfer. So the initial rate of heat transfer, I know the temperature of my sphere is at 90 degrees. So the delta T is going to be between 90 degrees and 20 degrees C. And plug and chug, we get 7.9 watts. Whether it's big or small, whatever it is, but we have been able to give a number, because we're engineers, or very soon you will be, and say, this is the amount of energy getting out of the sphere. It's quite amazing. Everybody has common sense and intuition to know that it's cooling. Only because you're taking this class, you're able to say, and it's losing that amount of energy, 7.9 watts. All right, awesome. What is this good for? It's good for many things. Let's go one step at a time. Okay, so what is the initial rate of cooling? Right? What is the initial rate of cooling in this problem? Now I just asked what is the rate of energy loss? But how many degrees does it lose? How many degrees per second does the sphere lose? Even more interesting, because the watts, those are very difficult to measure. But if I say, how many degrees per second? You go to Home Depot and spend $20 in a multimeter with a thermocouple, maybe more, 50, I don't know, something like that. And you put it there and you measure it. And if you have a fancy oven that has something to measure the temperature of the food, you stick that in and it works. And it's going to give you the degrees per second. My question to you is, before we measure it, can we as engineers make an estimate of how fast it's going to be cooling? And the answer is, oh yeah. So for this, we need to do an energy balance, because we know the energy that is being lost, but we need to see how it translates into degrees, that is energy stored, the Q stored. So in our energy balance, we have to make first our control volume, which we have here. We have the sphere and the control volume just outside. Easy peasy, but in problems that you might face in your professional life, they might be a little bit trickier, but this is very simple. So the sphere is hot, the fluid is cold, so I'm going to claim that there's no energy coming in, and typically there's none, right? The sphere is not generating heat, so I'm going to say no Q gen. So I have the Q out equals the Q stored. Okay, excellent. It doesn't need to be like that. It is like that only because I said no Q in and I said no Q generated. We're going to see on Friday what happens when Q generated is not zero, and it's super interesting. So, okay, I know my Q out, and let's calculate the Q stored. Q stored, based on the formulas we saw in the first week, is the derivative of mass times enthalpy with time. In this case, our control volume is a closed control volume. The sphere is not evaporating, it's not melting, it's not losing any mass through its surface. So mass is constant, and we have is derivative of enthalpy with time. This is math. Math, you know, right? But the whole point of this math, that is just Calc 1, is to make formal the things we already know. All right, and we know that mass is volume times density, and enthalpy, the copper does not melt, has no phase change between 90 degrees and 20 degrees. So it would be specific heat times temperature rate. In this case would be a cooling rate. Right, and we have taken very small steps in week 1, making an energy balance. And actually, I'm not even putting anything else right there, right here. I'm not even using a heat transfer mechanism. This is just an energy balance. And oops, what happened here? So, okay, so, and okay. And so if now I include the energy balance, which is what we had done just in the previous step, is area times heat transfer coefficient times the difference in temperature, we end up with this. We can end up with equation 12, and we can solve to end up with equation 13. Right, and equation 13 says the cooling rate, the rate at which temperature is changing, is given by this expression here, right? That relates to the area and the heat transfer coefficient, to the difference in temperature between the surface and the fluid, to the volume, density, and specific heat. Many of you might have heard, especially guys in materials, about the surface to volume ratio. Here it is. Here's surface to volume ratio. Surface is AS over volume. All right. So if I plug in the numbers that all were like all numbers we had seen before, we get that the cooling rate is 1.21 degrees C per minute. And it has a minus sign because it's cooling, right? Temperature, as time goes on, temperature is lower and lower and lower. So it's a negative slope. And this is what comes here, right? So look at this. Without doing any math, we know what temperature the sphere starts, and we know what temperature the sphere finishes. No math involved. Then, with a tiny bit of math based on our knowledge of heat transfer mechanisms, we can know what the rate of energy loss is in the sphere. That's pretty cool. We're talking about watts, but watts are very difficult to measure. And then with one more step based on an energy balance, we can say, okay, you know what? These watts we were talking about mean 1.21 degrees C per minute. And by the way, if you are lucky enough to have a 6 centimeter copper sphere at 90 degrees C, this number that I put here is more or less what you would see. And if it is not exactly what you would see, it's typically because of measurement errors. Also in this case, we use a very approximate H, right? But these equations are not Mickey Mouse. These are the real thing. These are the equations used to calculate spaceships eventually. Okay, so I have another question, and I would like to hear from the first of you your thought. So is the cooling rate, this cooling rate we calculated, 1.21 degrees C per minute, is it constant or not? Of course, thank you very much. Thank you. Of course, it's not, because eventually it's just a matter of time we would like break below 0 Kelvin, right? If it was constant, of course. And we know eventually it's going to stop cooling when it's at 20 degrees C. So we know that the cooling rate in absolute value is going to decrease. It's going to start cooling fast and then cooling slower. You already can imagine in your mind, and if you don't, it's okay, but those who are anticipated, if I were to make a chart, I would see some sort of an exponential decay, right, in which it starts cooling down more or less fast and eventually cools down slower. Let's see if we can make this exponential decay here. Okay, so we would have if this is time and this is temperature, at time 0, I know that this is 90 degrees C for the sphere. And I know when time is infinite, we're going to reach 20 degrees C. All right, eventually we're going to be moving. See the. We're going to eventually be flatlining here, and we're starting here. Now, how much imagination does it take to see what the evolution would be? And now, no math involved, right? It's going to be, oops, a curve like this. Wow. Hold on a second. This is trying to. Here. It's online teaching, it takes some learning for everybody. Okay, good. So I don't know why this thing went crazy on me. Let's see this. But we are going to see something like this. That's the evolution we're going to see in this sphere. And we just calculated that this slope here is this is 1.21 degrees C, and this would be 1 second. Excellent. Excellent. So the whole point here is how we turn into like this calculus and this math you have seen and this physics you have seen, but a year from now, a year and a half from now, you're going to be engineers, right? How do we start like becoming engineers and expressing this all this information and this knowledge, some intuitive, some formal, into an engineering means of communication? Okay, so let's go back to our notes. And in the notes, I mentioned here the things we just did. That we know where the curve starts. We know where the curve finishes at long times. We know the cooling rate at the beginning, and this is important. Let me show you something. You see in this curve the slope in the slope near zero. The slope here right near zero. All right, whatever. It refuses to cooperate. So the slope near zero is not a zero slope, and it's not an infinite slope. It's this one slope here that is 1.21. So in a normal class, we would pay attention to that. I don't know what 1.21 looks like, but I know what 0 looks like, and it's not 0. And I know what infinity looks like, and it's not infinite slope. That's very important. So we know the slope here is 0. The slope down here is 0. The slope here is not 0. And in between it changes. Okay, back to the notes. Okay, so we know this about the curve, and of course here we have the curve again in your note. Now, if you're at work, nobody's going to ask you, okay, tell me how many watts is losing, or tell me how many degrees per second is losing. With the type of questions you would be asked is, how long does it take to cool down? That is a standard engineering question. How long does this sphere take to cool down? And this question is a question that to some extent is trivial. Yeah, the sphere is cooling down, okay? How long until it cools down? Sounds like a fair question, but funny enough, it's not a fair question, because define cooling down, right? And do you say when it cooled down to 99% of the final value, to 95%, 98%, when it cooled down half the way to the final temperature? I know for sure that it takes infinite to reach the 20 degrees exactly. But I know it's not going to take infinite. In reality, something's going to happen. This question that is trying to give a concrete number, an engineering number to something that doesn't have a clear breakpoint, that is a curve that is cooling down slowly. What this question is asking is for something that is called a characteristic time. So a characteristic time is a time that characterizes a process, but it's not a time at which anything in particular happened. In this case, I mark this characteristic time here. And if you see, nothing in particular happened there, huh? Nothing. And nothing in the curve. There is nothing that you can say, oh, I choose this point for this reason. There are many ways of defining the characteristic time. Right? For example, in radioactivity, they use the half-life of an element, that is how long it takes to decay to half its original radioactivity. In fluid mechanics, they use 99% often. All of those are equally good. In this class, we're going to use a definition of characteristic time, and later on you'll see characteristic length, characteristic distance, that is very helpful for making calculations. This is what I use in my professional life too. I highly recommend it. But I understand that other people might use other ones. In this class, this is the one we will use. And this definition of characteristic time that we will use in our class is, if I were to get this slope at the starting point, and I'll try to annotate here. So let's see how this goes. Okay, here we have a characteristic, a starting point, and we have a slope. I mark the slope at 0, and man, sometimes you can't win. Okay. All right, going back to our zero slope, sorry, our slope at time zero. I extrapolated until this curve intersects the steady state final temperature. At this point, this intersection this let me get the chat. This intersection we're talking about here, this is what defines the characteristic time. And by the way, it makes perfect sense, right? Just like many other of the definitions also make sense. So if this is our characteristic time, and when we are asked, how long does it take to cool down? We're gonna say, well, there's no exact point at which it can be considered cool down, but for time, this time characteristic time is already well approaching the final temperature. Okay, so let's calculate this characteristic time. We know that the slope would be T infinity minus T0, right? Final temperature minus initial temperature divided this TC, because that's the definition of the slope. And we also know that I can solve for this, I can solve for the characteristic time out and put in this cooling rate. And here in the notes, I also make it clear before, right? The derivative of temperature with time is shorter to write as T dot, meaning derivative with time. So, and this cooling rate, we have calculated it just in the previous step. So we would have minus 20 degrees C, that is a final temperature, minus 20 degrees C minus 90 degrees C, right? That is the initial temperature, divided by the cooling rate, which was negative, right? Was this 1.21 degrees C per minute. And what did we get? Almost 58 minutes. So this sphere that is originally at 90 degrees and is left to cool in stagnant air by natural convection would take more or less 1 hour to cool down, right? And that's the answer. If people say, aha, does it cool down to 21 degrees or to what? This is a good ballpark number to start. Now, if somebody says, okay, but I want to know exactly to what temperature it cools down, we can also do it. And this is the way we do it. Okay, let me see. As I prepare for that, and I'm looking at the chat, please take a look at the notes. This will be included in the quiz on Wednesday next week. And I will not be asking filling the blank questions or anything like that. We'll be doing calculations, right? And we'll be identifying curves that might be right or wrong, or things like those, all based in these concepts. Okay, so going back to our analysis of the cooling of a sphere, look at this. If we get this equation that we had in the previous page, equations 13, here, this equation we did when we tried to calculate the initial cooling rate, right? we can redistribute this equation that is a combination of Q stored, this one on the right. This one on the right is Q stored. The one on the right is Q stored, and the one on the left was Q out by convection. We end up with this expression. Now, if I rearrange this expression without changing anything, just exactly as it is, we end up with this expression here. Now, this expression, that's a differential equation. And much of what you're going to see in this class, and it's one of the reasons why it can be a challenging class, is because all these things we know from our intuition or common sense or these energy balances that look so innocent initially, when we put it all together, then end up being a differential equation. But it's good that we, at least with a differential equation, we can calculate things, because the sphere is changing temperature as it's cooling down. And as it changes temperature, that means it's changing how much heat is losing by convection. The problem is extremely difficult. It took 200 years for people to figure out heat transfer, and it comes to you in one term, right? But because you had this background of some basic math, when we see this, we recognize this differential equation. And this differential equation, before we solve it or do anything else, let's look at some aspects. It has only one variable, right? That is time. And that's very important to have this kind of accounting of what the variables are. Only one. So it's an ordinary differential equation. Those are the easiest ones to solve. Doesn't mean they're trivial, but they're the easiest. And then is linear. If you see, we have a derivative here. There is no exponents there, so it's good. We have temperature here without any exponents. It's good. So in that case, it's called a linear equation. If we were to do this problem with radiation, here we would have a T to the 4, and it's not linear anymore. What is important about being linear are the easiest to solve, right? So ordinary, linear, we're making the problem. Well, this is, thank God, reality is represented by this equation, and it's among the simplest to solve. Now, when this equation was equal to 0, that's called a homogeneous equation. But this equation is not equal to 0, right? So this is a non-homogeneous equation. We have this term here that comes from moving terms around in the previous equation 13. So if I have a first order differential equation, ordinary differential equation, I would like to see if somebody tells me through the chat, how many boundary conditions do I need for this equation of first order? Looking at the chat here. How many boundary conditions do I need in this case? Anybody remembers? Well, it's in the notes. So, yes, thank you. Thank you very much. One, first order differential equation, one boundary condition. Second order differential equation, guess what? Two boundary conditions, right? And we'll deal with those later. But right now, we have an equation that is linear, or is ordinary, is linear, needs only one boundary condition. What is that boundary condition going to be? Initial temperature. Initial temperature is here. You might wonder, okay, where does final temperature go? It's right here. Here is at infinity. That's where it goes, is this non-homogeneous part. And in this equation, we see some independent variable that was time, and only one. That's why it's ordinary. And we have a dependent variable, and that is temperature. Temperature depends on time, and it's a variable. Variables are things that within a problem can change. For example, in our problem of the sphere, temperature is changing all the time as time changes. Now, these equations also have parameters. And these parameters, in math, they focus so much on you solving the equation, but this engineering side of the equations, very often they move very quickly. So variables and parameters are very different. Time is a variable, temperature is a variable, but the surface area of the sphere, that's called the parameter. In the problem, time and temperature are changing, but the area of the sphere is the same. Same with the convection coefficient H. In this case, we assume is constant. Does not depend on the temperature and does not depend on time. Parameter. Density of the sphere, specific heat, volume of the sphere, the temperature of the fluid outside, the temperature of the initial temperature of the sphere. All these things are numbers that do not change with time or temperature. And these are the parameters of the problem. So this equation is an equation that would give us the answer to, all right, you tell me it's going to take about an hour to cool down. But I know it does not cool down to exactly 20 degrees. So this time constant you give me is a time constant to what temperature exactly, right? Dang, I just gave an answer. I was so happy with it. And now they are asking us something much finer. To give an answer to that question, what is the exact temperature after some time, we need to solve this equation. Because this equation is very easy to solve, we will solve it. And I'm doing it here, the way they do it in the book. There are many ways of doing it. So I'm doing what the book is doing. So you can read it and we are speaking with the same voice and you have many resources from where to get the same information. So the first thing we do is a change of variable. And t minus t infinity, we're going to call it theta. So, and this group that appears here, right? You see the AS H over V rho C appears twice. I'm going to call it K, whatever it is, K. And so if we substitute these two changes, this is a change of variables and this is a renaming of the parameters, putting them all together, we end up with this equation here, equation 21, which is exactly the same as before. No simplification, exactly the same thing, but it looks a lot simpler. Among other things, you know what is cool about this equation 21? It became homogeneous. That is even simpler than the non-homogeneous. So now we have, you cannot possibly have a simpler differential equation than this. It's linear, it's ordinary, and it's homogeneous, right? Here is the one boundary condition that says theta, so t minus t infinity at time 0 is theta 0, which obviously is t 0 minus t infinity. And so we can, I see it's time. So before I start on this, let's stop here. Please do yourself a favor and take a look at these notes. And if something is not clear or if something you like to refresh, let me know by email, any way you want. I'm going to take a 2-minute break and we're gonna join the office hours no later than 2. I might be back in even sooner. Please join me. It makes me happy to talk with you and we turn on the cameras and we get to know each other. Let's stop here. Thank you very much.